Hi. In this video, we're going to talk about 10.1, the language of hypothesis testing, and it's actually going to be broken into two videos due to length. So there'll be a part 1 and part 2. This is part 1. We're going to be doing hypothesis testing in chapter 10 and in chapter 11. So we have a section where we talk about the language and the procedures for hypothesis testing, and then we'll use these same vocabulary terms and these same procedures in the rest of the sections that we do. We'll cover two types of single sample hypothesis testing in chapter 10 and three types in chapter 11 that deal with two samples. To start with, we'll talk about what a hypothesis and a hypothesis test are. A hypothesis is a claim or a statement about a characteristic of one or more populations. And like I said, more populations comes in chapter 11 when we talk about a couple of hypothesis tests on two populations. A hypothesis test is a procedure based on sample evidence and probability used to test claims about a characteristic of one or more populations. So in the hypothesis test, we will test the hypothesis to see if there is enough evidence to support the claim. Because we're using sample data to test the claim, we cannot say with 100% certainty that the statement is true. We can only determine if the sample data support the claim or not. So we start with the components of the hypothesis test, and we begin with the null hypothesis and H1, which is the alternative hypothesis. And sometimes you'll see this written as HA, but we will use H1. So HO is the null hypothesis, and H2 is the alternative hypothesis. And these are simply statements. So HO and H1 don't equal anything. They are the names of the two statements that we'll be looking at. In chapter 10, we're going to be testing a single sample, and we're going to be testing hypotheses about the mean or about a proportion. We will not do the hypothesis testing on the standard deviation. The null hypothesis, denoted HO, is a statement that the value of the population parameter, and that will either be mu, the mean, or p, the proportion, is equal to some claimed value. During the test, you assume that HO is true until the evidence indicates otherwise. In the conclusion, you will either reject HO or you will not reject HO. We never ever use the word prove, because we're not proving anything. We're just finding whether the evidence supports the statement in the claim or not. So for the two types we'll be doing in chapter 10, this is what the null hypothesis will look like, and this will be a number that we get from the problem. When we're testing about a hypothesis about the mean, HO will look like this. Mu equals some number that we get from the problem. And when we're testing a hypothesis about a proportion, it will look like this. P equals, again, a number that is given in the problem. Always, always, HO always contains an equal. And we never say that HO is equal to something. It must state something about a parameter. So we don't say HO equals 5.2. That is a big no-no. The alternative hypothesis is the claim that we're looking for evidence to support or not support. We determine from the test whether the evidence supports the claim or not. And this will be H1 for our purposes, but sometimes you will see it as HA. It's a statement that the parameter somehow is different from the value in HO. It's a statement that we're trying to find evidence to support. It cannot contain the equal sign, and it must be true if HO is false. They are mutually exclusive. You can't kind of sort of have both of them be true. So these are various ways that H1 can look. Remember, in the ones we're doing, HO will always be one of these depending on which parameter we're testing. But we can have various types of H1 statements. If we're testing for the mean, we can say that the mean is simply not equal to the number in HO. Or we could say that the mean is greater than that number, or we can say that the mean is less than that number. And it depends on the way the question is worded and what we're actually looking at in terms of the claim that's being made. And the same thing is true for the alternative hypothesis in when we're testing a proportion. We can be testing the claim that the proportion is simply not equal to the number that is in HO, or that it is greater than the number that's in HO, or that it's less than that value. So it could be any of those three. And which of those three, it's important to know, be able to tell from the problem which one you're dealing with. It comes from the wording, and you just have to be looking for some keywords. But how we perform the test on the calculator is completely dependent on which of these three it is. Is it the not equal? Is it the greater than? Is it the less than? And each one of these is one of these two. A two-tailed is the not equal. So this is the two-tailed. This is the right-tailed. And this one is the left-tailed. So if we have a greater than symbol, that is a right-tailed test. If we have a not equal to, that's a two-tailed test. And if we have a less than, that is a left-tailed test. So the direction that this inequality symbol points is which tail we're looking at. This points to the right, so it's a right tail, left to the left tail. And when it's not equal, it is a two-tail. And what's going on here is we have in the two-tail, the not equal to, well, it could be not equal to at either end. So that's how it's a two-tailed. The probability that it's not equal could just come in either direction. For a right tail, all of the probability that it is greater than the value we're looking at would have to be down here in the right tail. And for left tail, all of the probability that it's less than the value we're looking at would have to come somewhere down here in the left tail. And your calculator will draw this picture for you. You'll see that there's an option for drawing, and it will show you a picture. So a two-tailed test occurs when we have the not equal to symbol, a left tail when we have the less than symbol, and a right tail when we have the greater than symbol. Alpha is the probability that we're looking for to determine that it's that the probability is very low that HO is true. And in a left tail test, all of that probability is down at this end. In a right tail test, all of that probability is at this end. And in a two tail, it's split between the two. All right. So we're going to identify a couple of these HO and H1 statements and then determine which type of test we're doing. The percentage of male voters is less than 40%. So percentage, this is going to be a proportion. So we'll use P. And remember that null hypothesis always has equal. And 0.40 is how we would write 40%. We write it as a decimal. This says less than. That's pretty obvious. So this is how we would write the alternative hypothesis. That's the claim we would be testing. And because this points to the left, this is left-tailed. The next example, the mean amount of water in a bathtub is more than 124 gallons. So again, this is a mean. So we've got mean and always equal. In the null hypothesis, 124 is the value. And this is saying that we're testing the claim that it's more. More would be greater than, so the mean is greater than 124, and this would be a right-tailed test. The alpha level is typically given in the problem. If you were designing a hypothesis test as a statistician or during a research project, you would choose an alpha level based on a lot of factors, but we're going to be given that in the problem. The critical value is a value that comes on the Z or the T distribution, and it's the cutoff for those shaded areas you saw in the distributions that I drew on the previous page. The cutoff is the critical value. We are not going to do the test by using a critical value, but we'll look at a little bit at what that means. But we're actually going to use a different method for performing the test. So the level of significance is the probability of making a type 1 error, and we'll talk about what that means. So type 1 error is the probability of that is alpha. The critical value is any value that separates the critical region from the values of the test statistic that do not lead to a rejection of HO. So it cuts off an area where the HO, the null hypothesis, is so improbable that we reject it. The critical region is the set of all values of the test statistic that will cause us to reject HO, and that region is cut off by this critical value. So again, on the drawings that I made over here, the critical value is the cutoff point for the area that I shaded in the tails. In a two-tail test, that probability again is split evenly between the two tails. In the left tail, it's all in the left, and in the right, it's all in the right. Now, here's a table of critical values, and we've seen some of these two-tail ones before. When we did a confidence interval, we saw some of these same values because these are very closely related. You don't do a confidence interval with just a right or left tail because obviously it's an interval that has two ends. Finding the critical Z values for a hypothesis test about a population proportion. If we're doing, if you have to find that, if it's a two-tail test, it's in this column, alpha equals 0.01. It's going to be plus or minus 2.575. So the table just gives it to you, but we don't perform the test using this, so you really won't need to use it other than to just kind of know where it comes from. In a right tail test with alpha equals 0.05, here's 0.05. This is right tail, so it's going to be 1.645. Notice that for the right tail, all the values are positive. For the left tail, all the values are negative. And for two tails, it's the plus and minus of the same value because it's evenly distant from the mean on that distribution. Calculate and state the appropriate test statistic. This is actually going to be given to you from the calculator, so you don't need to worry about these formulas here. This is not something that you will need to do by hand. Thank goodness. We will just do this on the calculator, and it will give you that value. The test statistic comes from your data. These are the critical values, the cutoff points, and then in this method of testing, you would find the value that comes from your data, and you see if it's beyond that critical value. In other words, is it outside that line that we drew? Because we're not going to use this method, we aren't going to worry about these. The calculator will give it to you. If you're asked for it, just copy it down. And then draw the appropriate graph and label the rejection region. This is something that the calculator will show you a little graph like we drew on the previous page, and you don't need to do anything other than copy it down if you're asked for that. The p-value, this comes from the calculator as well, and this is actually the method we're going to use to perform the test. So the p-value is the probability of getting a value for the test statistic that is at least as extreme as the one found in the sample data. So in other words, when you have your data and you put it into the calculator, it determines what is the probability. If HO, the null hypothesis, is true, what is the probability that you would get this value from your sample? And if it's very small, in other words, if the probability that you would get a sample with that value, if that probability is very small, we reject the null hypothesis and say, okay, it must not be equal to that value because it's extremely unlikely or unusual, as we've said before, that we would get this value if this other value is really true. So small p-values less than alpha mean results are unusual and there's a significant difference from the value in HO, and we reject. So small values, we reject HO. And a little saying that a colleague of mine came up with. Where am I? I'm sorry, I lost my place. And large p-values more than alpha mean that the results are not unusual and there is no significant difference from HO, so you should not reject. So we do not reject if p is large. And what do we mean by p is small or p is large? We compare p to alpha because alpha is the value that we've set for unusual. And anything that is less than alpha, if p is smaller than alpha, we reject. If p is larger than alpha, we do not reject. So p is greater than alpha, do not reject. P is less than alpha, we reject. So if we look here at this example, state the appropriate decision, reject HO or do not reject HO. And we're going to look at the p-value approach. This is the one we're going to be doing, so this is what you really want to focus on. The classical approach gets the same result. You're just looking at the test statistic rather than the p-value. They are completely related, but we're going to do this method. So if the p-value is less than alpha, reject HO. If the p-value is greater than alpha, do not reject HO. And then we write a conclusion, also sometimes known as a decision. And when we reject HO, we say there is sufficient evidence to conclude that, and then we just restate whatever the claim was. And if we do not reject HO, there is not sufficient evidence to conclude that, and then we restate whatever the claim was. So if the claim is the proportion of women who smoke is less than 0.35, and we reject the claim. So if we reject HO, then we're actually determining that this is what the evidence supports, that the proportion of women who smoke is less than 0.35. So we say there is sufficient evidence to conclude that the proportion of women who smoke is less than 0.35. So we rejected HO. HO would have been that the proportion equals 0.35. The claim was that the proportion is less than 0.35. We didn't prove anything, but the evidence supported this. So when we reject HO, the evidence supported this, the claim, and this is how we would state that. In this other example, the claim is the mean number of peanuts in an 8-ounce jar is not 200. So this is a mean. So HO would be the mean is equal to 200, and H1 would be the mean is not equal to 200. We don't have to say whether it's more or less. In fact, if this is what we test, we can't say it's more or less. All we can say is that it is not equal to this if we conclude that we reject this. But this says do not reject HO. So we would say there is not sufficient evidence to conclude that the mean number of peanuts in an 8-ounce jar is not 200. There is not sufficient evidence to conclude that the number isn't 200. The evidence supported that it is 200. Our sample may not have given us exactly 200, but remember, this was just one sample out of the whole population. It's not going to necessarily be exactly 200, but it's within the margin of error. So if it's within the margin of error, and that's determined by our alpha and the parameters of the problem, we would say there isn't sufficient evidence to conclude that it isn't 200. If, under a given assumption, the probability of an observed event is exceptionally small or unlikely, we say that the result is statistically significant. When results are found to be statistically significant, we have evidence to reject the null hypothesis. So remember, we're looking for evidence for the alternative hypothesis. This is the status quo. We are looking to see if the evidence supports this right here. All right, I'm going to pick up in the next video with the next part of 10.1, starting to talk about type 1 and type 2 errors.